സ്ലീപ്പ്. അതുകൊണ്ട് ഈ മാട്രസ് അല്ല, വാങ്ങുക സ്ലീപ്പ് കമ്പനി മാട്രസ്. അതുകൊണ്ട് ഈ മാട്രസ് അല്ല, വാങ്ങുക സ്ലീപ്പ് കമ്പനി.
ഹലോ ഹലോ കേൾക്കാം. ഹലോ ഹലോ ഹലോ
ഹരി, ഹലോ ഹലോ ഹലോ
കേക്കാം കേക്കാം.
ആ
ഇപ്പൊ ക്ലിയർ
കുഴപ്പമില്ല.
ആയല്ലോ.
ഏ
ഇപ്പൊ ക്ലിയർ ആണ് സാർ
ആ
പറഞ്ഞത്.
ക്ലാരിറ്റി പ്രശ്നം ഉണ്ടായിരുന്നില്ല.
ആ
ഒരു ഒരു നോയ്സ് ചെറിയുണ്ട്.
നോയ്സ് പോയപ്പോ
ഈ ഫാനിന്റെ ഒക്കെ ഉണ്ടായിരിക്കും.
ആ ഹാ 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 അത് സാറ് വരുമ്പോ ക്ലിയർ ആക്കണ്ടേ അത്.
ഈ ബോക്സിൽ മാത്രമാണുള്ളൂ.
പക്ഷെ ഇങ്ങോട്ട് നോയ്സ്
ഇതിന്റെ
പ്രശ്നം
ഇച്ചിരി
കാണിക്കുന്നില്ല.
കുറച്ചിട്ടായി ഈ ഇതിന്റെ ഔട്ട് പ്രശ്നം.
സാറ് പറയുമ്പോ ഒരു ഇത് നോയ്സ് ഒന്നും വരുന്നില്ല, ക്ലിയർ ആയിട്ടാണ് ആ മൈക്കിൽ കൂടെ പറയുമ്പോ.
അത് ഞാനേ മൈക്കിന്റെ തൊട്ട് മുമ്പിൽ നിന്നിട്ടാണ്. മറ്റേതെല്ലാം വയർലെസ് മൈക്ക് ആകുമ്പോഴേ കറക്റ്റ് ആയിട്ടുള്ള പിടുത്തം ശരിയാവില്ലായിരിക്കും.
അതെ അതെ.
ഇത് വയർലെസ് മൈക്കിൽ നിന്നാണ്. ഇതിന് ഇച്ചിരി കുറവാണെന്ന് തോന്നുന്നല്ലേ വോളിയം?
അതിന്റെ ബാക്ക്ഗ്രൗണ്ട് എന്തോ ഒരു പ്രശ്നമുണ്ട് സാറ് പറഞ്ഞേ.
പക്ഷെ ഇവിടെ ഇപ്പൊ എല്ലാരും സ്റ്റേജിൽ ഇവിടെ വന്നിട്ടാ പറയത്തുള്ളൂ. കുഴപ്പമില്ല.
കുഴപ്പമില്ല.
ഇത് സ്റ്റുഡൻസിന് പറയാനായിട്ടാണ് ഉപയോഗിക്കുള്ളൂ എന്ന് തോന്നുന്നു. അല്ലെങ്കിൽ കോമ്പയറിംഗ് ഉണ്ട്. കോമ്പയറിംഗുകാര് പറയും. അപ്പൊ അവരോട് ഇപ്പൊ എങ്ങനെയുണ്ട്?
എപ്പോഴും പോരാ.
ആണല്ലേ. വോളിയം ആണോ കൂട്ടേണ്ടത് അതോ?
ഓളിയം അല്ല സാർ, ഓളിയം ഓക്കെയാണ്. പക്ഷെ എന്തോ ഒരു ബാക്ക്ഗ്രൗണ്ട് ഒരു വോയിസ് ക്ലിയർ ആവണില്ല. മറ്റേ സാർ നേരത്തെ പറഞ്ഞൊരു
കുഴപ്പമില്ല, ഇത് മതി എന്നാ.
ഓക്കെ
ശരി. ഹലോ
ഓക്കെയാണ്.
വേറൊരു മൈക്കാണ്, ഞാൻ ഓരോന്ന് നോക്കാന്ന് വെച്ചിട്ടായിരുന്നു. ശരി. ഹലോ ഹലോ
കേക്കാം.
ശരി.
जन गण मन अधिनायक जय हे भारत भाग्य द्राविड उत्कल जन ഒരു കരുണ ജന്മാസാരധാരകൾ ചൊരിയുമംബികെ പർജന്യ ദേവതേ സുരുചിരോദാര സന്താന ശാഖിയ കരികലപ്പകൾ കാളകൾക്കൊപ്പമായി വരിവരിച്ചാലു കീറിനിങ്ങിടവേ ധരണിയുൾ പുല്ല സസ്യഫലാഢ്യയായി ഹരിതരോമാഞ്ച കമ്പളാഭോഗയായി മനുജ വിജ്ഞാന സീമാ വികാസത്തിൻ അനുസൃതമായ സൗരഭ്യ സിദ്ധികൾ അവികലം വിതയ്ക്കുന്നു വിത്തുകൾ
A warm good morning to one and all. It is my honor to welcome you all to this one-day seminar on how agricultural management affects emission of nitrous oxide and nearly forgotten greenhouse gas, organized by IQAC Kerala Agriculture University. We are privileged to have us with a distinguished expert who contribute to science, agriculture, and environmental research. I extend a special welcome to our chief guest, Dr. B. Ashok IAS, Honorable Vice Chancellor of Kerala Agriculture University, who will be delivering the inaugural address. His extensive experience in academia, governance, and policy making has shaped sustainable agricultural and environmental policies. A warm welcome to our guest speaker, Professor Eric A. Davidson, Fulbright Fellow at the University of Maryland, USA, a leading scientist in biogeochemistry and environmental sustainability. His work has significantly advanced our understanding of greenhouse gas emissions and climate change mitigation. I also take this opportunity to welcome Dr. P.U. Namir, Dean, CCCES, who will be presiding over the session. His leadership and vision have been instrumental in fostering academic excellence at KU. It is my honor to introduce Dr. P. Indira Devi, ICA Emeritus Professor, and she serves as Special Officer at CCCES. A Fellow of Indian Society of Agricultural Economics, she has over 33 years of expertise in agricultural research and teaching. She previously served as a Professor of Agricultural Economics and Director of Research at KAU, and is a recipient of prestigious awards, including the Ford Foundation Relationship and the Professor Ramesh Chandra Agarwal Award. Finally, I extend a warm welcome to all the faculty members, researchers, students, and distinguished guests who have gathered here to be a part of this enlightening discussion. Let us now begin the seminar with an invocation song.
ഗുരുനിധാ ഘോഷണതപ്തമാം ഭൂമിയെ ഒരു കരുണ തൻ ആസാരധാരകൾ ചൊരിയുമംബികെ പർജന്യദേവതേ സുരുചിരോദാര സന്താന ശാഖിയാ കരികലപ്പകൾ കാടകൾക്കൊപ്പമായി വരിവരിച്ചാലു കീറി നീങ്ങിടവേ ധരണിയുൾക്കൊള്ള സസ്യഭരാഢ്യയായി ഹരിതരോമാഞ്ചകമ്പളാഭോഗയായി മനുജവിജ്ഞാനസീമാവികാസത്തിൻ അനുസൃതമായ സൗരഭ്യസിദ്ധികൾ അവികലം ശാസ്ത്രചക്രവാളങ്ങളിൽ അവിടവീടെ വിതയ്ക്കുന്നു വിത്തുകൾ പുതിയ ദീപം കൊളുത്തുക നാളത്തിൽ പുതിയ ജീവൻ തുടിക്കട്ടെ നിൽക്കുമേ അരിയ സൗഭാഗ്യധാരകൾ കക്ഷയ
To officially commence the session, I now invite Dr. P.O. Namir, Dean of CCCES, to deliver the welcome address, a visionary leader and a guiding force in our academic journey. Dr. Namir has been instrumental in fostering excellence at our institution. His dedication to academic and research excellence has made today's event possible. Sir, we sincerely thank you for your guidance and support. Please take the stage to extend your words of welcome.
Thank you. And you guys also can be seated. Okay. All right. So a very good morning to all assembled here. The chief guest of the day, Professor Eric Davidson, the Director of Appalachian Laboratory of University of Maryland, United States of America. The president of today's seminar, Dr. B. Ashok, the Honorable Vice Chancellor of Kerala Agricultural University, sir, has joined online. We also have Professor K. Pradhaban, the Vice Chancellor of D.Y. Patel Agriculture and Technology University, Kolhapur, who has also joined online. We have Professor Indira Devi, the former Director of Research and also the ICAR Emeritus Professor, who is here with us. Dear faculty members, the officers of the university, my dear students. We have all gathered here today to listen to the seminar by Professor Eric Davidson, who is the Director of Appalachian Laboratory of the University of Maryland and also the Principal Scientist at Spark Climate Solutions. His research includes terrestrial nutrient cycling, greenhouse gas emissions from soil, global biogeochemical cycles, and sustainable agriculture. He is a past president and fellow of American Geophysical Union, a fellow of the American Association for Advancement of Science, and a Web of Science highly cited researcher. Davidson was a Jefferson Science Fellow, a program administered by the U.S. National Academies of Science, Engineering, and Medicine, where he served as a science advisor to the Office of Environmental Quality at the U.S. Department of State. He is a lead chapter author on global nitrous oxide assessment by the UNEP, that is United Nations Environment Program. He currently serves as senior editor for AGU Advances. Davidson received his PhD from University of Forestry at North Carolina State University and worked as postdoc researcher in soil microbiology at the University of California and at the NASA MS Research Center. He worked for 22 years at Woods Hole Research Center, including a term as president and executive director. He published, in addition to several peer-reviewed journals, 2 books for general public on environmental economics, namely You Can't Eat GNP, which was published in 2000, and the second one, Science for a Green New Deal, Connecting Climate Economics and Social Justice in 2022. And today, he will be speaking on the topic, how agriculture management affects emissions of nitrous oxide, the nearly forgotten greenhouse gas. And I have great pleasure to, and consider it as a privilege, sir, to welcome Professor Eric A. Davidson to Kerala Agricultural University. A warm welcome to you, sir. Our Honorable Vice Chancellor, Dr. B. Ashok, has kindly consented to inaugurate this seminar. And for the benefit of Eric, sir, Dr. B. Ashok, our Vice Chancellor, is a veterinarian by training. He holds a double master's, one in water management from University of London, and a second one in political science from the University of Turin, Italy. His PhD is in media and communications from Amartya Vidyapeetham in Kochi. He has been a civil servant in the Indian Administrative Service since 1998 and has been holding several key positions in the state and central governments. He has 7 books to his credit, of which 2 are bestsellers, and published more than 100 research articles in peer-reviewed journals. He is a regular columnist and regular columnist in lead newspapers and magazines. In addition to being the Vice Chancellor of this university, he also holds an additional responsibility as the Principal Secretary and the Agriculture Production Commissioner in the Ministry of Agriculture and Farmers Welfare of Government of Kerala. He was also the first Vice Chancellor of Kerala Veterinary and Animal Sciences about a decade back. And his ministry is now implementing a World Bank aided project called Kerala Climate Resilient Agri Value Chain Modernization, which is his brainchild, which has a budget to the tune of 285 million US dollars. And I hope that Ashok sir will touch upon the highlights of Kerala project during his inaugural address. In spite of his exceptionally busy schedule, he has kindly consented to inaugurate this important seminar, which actually shows his academic inclination. And I have great pleasure, sir, in welcoming Dr. B. Ashok, our Honorable Vice Chancellor, who has joined online to this seminar. Welcome, sir. I must make a special mention about Professor Indira Devi, the former Director of Research, Kerala Agricultural University, who has been responsible for connecting us with Professor Eric, and who has come as a Fulbright Fellow in New Delhi. So it is through Indira Devi ma'am only, we managed to get Professor Eric to Kerala Agricultural University. So a special mention and welcome to you, ma'am. Well, we have Professor K. Prathapan, the Honorable Vice Chancellor of D.Y. Patil Agriculture and Technical University, based in Kolhapur in Maharashtra, who has joined us online. Welcome to you, Prathapan, sir.
Thank you. It's my pleasure.
And we have several of the university officers joined online and offline. We have Professor Kunyamu here, who is the Dean of the Faculty of Forestry. Welcome, Kunyamu, sir. And I also see several faculty members of Kerala Agricultural University. Extend a very warm welcome to all of you. Well, when we talk about climate change, and one of the first thing that comes to your mind is greenhouse gases. And among the greenhouse gases, one of the most discussed ones are the carbon dioxide and the methane. But then in today's talk, we will be Professor Eric will be highlighting on the nitrous oxide, which is sort of a kind of less paid attention greenhouse gas. So in that background, I'm sure that this deliberations today will be extremely useful for all who have assembled here. So with these few words, I once again extending my warm welcome to each one and one of you to this important seminar. Thank you.
Thank you, sir, for your inspiring words and for setting the tone for today's discussion. We are honored to have with us Dr. B. Ashok, IAS, Honorable Vice Chancellor of Kerala Agricultural University. It is my privilege to introduce our esteemed guest, Dr. B. Ashok, IAS, an eminent educationist, writer, speaker, and columnist. Currently serving as the Vice Chancellor of Kerala Agricultural University, he was also the founding Vice Chancellor of Kerala Veterinary and Animal Sciences University. A 1998 batch IAS officer, Dr. Ashok has held key positions including Director of the Central Department of Agriculture, Deputy Director at National Academy of Administration, Missouri, and faculty member at the IAS Academy for over 15 years. He has also served as Power Secretary CMD of KCB and Director of Water Resources, spearheading impactful reforms in the energy sector. Sir, I welcome you to give the inaugural address.
Can somebody confirm whether the audio is okay? Is it okay, the audio? All right, thank you. Thank you. A very good morning to all of you out there. Particularly the guest of the day, Professor Eric Davidson, our colleagues, Dr. Namir, Dr. Indira Devi, Professor Kunyamu, Dr. Prathapan, and all the other university officers attending this very important seminar and workshop, faculty and students. So my sense is, I'm extremely glad that you noticed me on this important visit, as well as the work of Professor Davidson, all the way from Maryland. And I was additionally glad to hear that he worked at North Carolina. I'm sure near the very famous Research Triangle Park in North Carolina, where I was fortunate to spend a few months in the neighboring Duke University in their Institute of Public Policy sometime in 2009. So it's an extremely interesting area to part of the world to be, with two very important universities operating out there. And I'm extremely glad that you are here with us today. I guess it is part of your Fulbright arrangement, and we consider it a great fortune and sort of our privilege to sort of listen to you in person. Visits like these are very important. Lectures give a lot of exposure to our students and show them the possibility of the range of work that is possible in laboratories across the world. And from my very limited knowledge, I don't claim any, forget in depth, even more than required familiarity on climate change. I handle it as an administrative subject. But I would think that Appalachian Laboratory is an extremely referred institution in several areas, from my very layman's understanding. So this we consider a very important opportunity. So it is unfair of me to sort of forget. I do not know why a workshop needs an inauguration all the time in our part of the world. We should not stand before you and the audience, and we will listen to you. I would just make this short point that Kerala is not a high emitting state, so to say, either from the data or it may not be that central to, because Kerala's agriculture is very few select crops in plantations, and some rice, some coconut, and some vegetables. So the most important thing to realize is Kerala is a food deficit state. It imports 50% of vegetables. Professor Indira Devi would have better figures, but 50% of at least the vegetables, and 60 to 70 to even 75% of the staples. It's not an agriculture heartland. The rest of India supports us because it is a high land valued, high labor valued state, which the production costs are not economic for a variety of crops. But the intention of the government is to sort of gain strength in agriculture as a value addition sphere, and an area where you can work on the agriculture. It has enhanced its earning potential by lifting the value chain and sort of gaining a clutch on exports, as well as in country and out of country. So therefore, that being the central strategy, we are closely looking at the ecological impact of our cultivation. Secondly, rice, of course, we have picked up as a key theater by trying out, experimenting with some early models, alternate wetting and drying, etc., to reduce the emissions which are attributed. So this is all I would say as an introduction. I'll be standing by, not necessarily in the video mode, but trying to absorb what you are telling our faculty and students. Such a pleasure once again. I am so glad to see Professor Indira Devi, Dr. Prathapan, and congratulations, Dr. Namir's team, for putting this together. So wonderful. Have a nice day. And for the sake of, since you said I should inaugurate, I'm saying that the workshop stands inaugurated. Thank you, and have a very nice workshop.
I now welcome Kunyamu sir onto the seminar. He has arrived late, but we are very honored with his presence on this program.
Thank you, sir, your invaluable insights for gracing us with your presence online. It is now my privilege to introduce our keynote speaker, Professor Eric A. Davidson. Professor Davidson is a globally renowned expert in biogeochemistry and environmental science. He has held esteemed position at the Woods Hole Research Center and currently serves as a professor at the Appalachian Laboratory, University of Maryland Center for Environmental Science.
His research has significantly advanced our understanding of greenhouse gas emissions soil-atmosphere interactions, and environmental sustainability. He has also contributed to science policy at the highest levels, including serving as a science advisor to the US Department of State. Beyond his research, he is distinguished author with works like You Can't Eat GNP and Science for a Green New Deal, which explore the connections between climate, economics, and social justice.
Sir, it is an absolute privilege to have you with us today. We now invite you to take the stage and share your insights. Sir, we are truly honored to have you here today. Sir, please.
Well, thank you for that very kind introduction. And truly, the honor is mine to be here today. And I want to thank Vice Chancellor Ashok for the kind words of introduction, and Dean Namir for helping organize this, and also Professor Devi for helping us make this connection and make this visit possible. I'm very pleased to be here and very honored to be able to talk to you today. If I could have the first slide, please. While I'm waiting for it to come up, the Fulbright Fellowship has been mentioned a couple of times already, and I just thought I would pause for a moment and mention something about this. This is called a Fulbright Nehru Fellowship that is a cultural exchange between the government of India and the government of the United States. Both contribute funding to this program called the U.S.-India Education Foundation. And there are currently around 100 American scholars in both science and technology and the arts, who most of them are early career. A few of them are the more senior scientists like myself, who are studying in India here now. And I believe there is a similar number of Indian citizens who are studying in the United States. And so this is something you may wish to look into. The program is widely acknowledged and advertised about the opportunities for Indian citizens, particularly scholars in early career scholars in the sciences and technology area. And I'd be happy to connect anybody to that office if they would like to get more information. So I'd like to start out on this topic of nitrous oxide by stepping back a bit and looking more broadly at the use of nitrogen. And this is a global perspective, and we'll focus more on individual countries later. But from a global perspective, on the y-axis here is teragrams of nitrogen. A teragram is 10 to the 12th grams, or 1 million metric tons. And this is production of reactive nitrogen. What do I mean by reactive nitrogen? Basically anything other than N2. 80% of the air that we breathe, of the atmosphere, is dinitrogen gas, which is unreactive. We breathe it in, breathe it out, we can't use it. There's a limited number of organisms. Those of you who study some microbiology are aware of this. Limited number of organisms that are capable of taking that N2O out of the atmosphere and converting it into a form that can be used by life. And we all need it for production of enzymes, for plants to produce chlorophyll, for building our muscles. It's absolutely essential for life. But there's a limited number of organisms that can convert that atmospheric nitrogen into a form that can be used by all forms of life. Prior to the Industrial Revolution, or at the time of the Industrial Revolution in the late 19th century, most of the nitrogen, of the reactive nitrogen entering the biosphere, was through natural biological nitrogen fixation in forests and in grasslands and various types of systems that are minimally affected by humans. That's the dark green part of the chart here. That has declined over time as we've converted forests and grasslands to agriculture. But still, it's a major part of the introduction. And this is only of the terrestrial biosphere, by the way. There's a similar amount that's produced through biological nitrogen fixation in the oceans. There's a tiny amount, the red line there, that's fixed by lightning. Lightning in the atmosphere can convert that dinitrogen gas into nitrate. The light green line is the cultivation of leguminous crops. So soybeans, groundnut, alfalfa, various pulses. They have associated symbiotic associations with the bacteria that can carry out that biological nitrogen fixation, often in nodules in the roots of those plants, and that helps provide nitrogen to those plants. And that has gradually increased over time since the Industrial Revolution. In yellow, you see the inputs from combustion of fossil fuel. There is some nitrogen in fossil fuel, not a lot, but a little bit, that gets released when it's combusted. Also in the internal combustion engine that we use in our automobiles, when that piston goes down and creates pressure on the gases that are in there, some of that nitrogen is oxidized to various forms and comes out the tailpipes of the automobiles and trucks that are using that fossil fuel. But the big change since roughly the 1950s is this big blue blob that you see there that I've labeled as ammonia, and showing that ammonia is formed from the combining dinitrogen gas, that gas that's in the atmosphere, 80% of the atmosphere, with hydrogen. And this is a process that we call the Haber-Bosch process. It was invented by German scientists and engineers around about World War I in order to help Germany attain munitions, because that ammonia can then be converted to nitrate and then be used for explosives. The N in TNT refers to nitro. So that was important then. It wasn't until after World War II that synthetic fertilizers began to be used in a big way. That was part of the Green Revolution that occurred in South Asia and Southeast Asia. And as you can see, it's projected to continue to grow. But so this has come, if you could advance to the next animation, this Haber-Bosch process is really one of the greatest boons in terms of human health, in terms of nutrition. that there's too little nitrogen being used, particularly sub-Saharan Africa, where the cost of a bag of fertilizer is beyond the means of most subsistence farmers, largely because of the additional costs of transport, because there are very few fertilizer production facilities in sub-Saharan Africa. So there are many places where farmers are actually mining the soil. In other words, they're pulling more nitrogen out of the soil in their harvest and exporting the harvest than they are returning back to the soil in the form of fertilizers or manures or mulch or any other kind of input to the soil. So this really is a story of too much or too little resource being available, and we need to pay attention to where we're referring to when we speak about that. Next slide, please. This cartoon is meant to make the point that nitrogen management is not the purview of a single ministry of any particular government. It's not just a problem of the Ministry of the Environment or only a problem of the Ministry of Agriculture. It also comes from energy. And also the nitrogen moves around from the atmosphere to the terrestrial biosphere to the aquatic biosphere. And it can be causing air pollution as PM 2.5 one day, and then rain out onto the soil and be affecting biodiversity the next day. And it can leach into the waterway and cause an algal bloom the next day. So it's continuously cycling, and it's going through various oxidation and reduction processes. I won't quiz you on the various forms on the right and which ones are oxidized and which ones are reduced, but that's the kind of thing that we learn about hopefully in microbiology classes, in biogeochemistry classes, to understand this variety of forms of nitrogen as it occurs, and each different form has a different kind of impact on human health and on the environment. Next slide, please. When we talk about the agricultural sector, I think it's useful to think about our nitrogen management as through a metaphor of nitrogen flowing through leaky pipes. On the left-hand side, we have all the inputs of nitrogen into our crop production system. This includes the synthetic fertilizers, it includes manure, it includes that natural nitrogen fixation in leguminous crops like soybean and groundnut. We grow crops, but that pipe production system of crops is a very leaky system. And that's represented by the holes in the pipe, out of which going upwards go the various gases, ammonia, N2O, NOx, and some going back to that dinitrogen gas in the atmosphere. Going below, we're looking at predominantly nitrate, but some other forms, dissolved organic nitrogen going into groundwater. Now, most of the crop production, most of the nitrogen in crops, most of our crops go to feeding our livestock. I think a lot of us don't recognize that only a very small fraction of our crops are actually consumed by us directly in the form of rice and bread and other staples and other vegetables and fruits. The vast majority is fed to our animals. And there you have another leaky pipe, because those animals only can convert a fraction of that crude protein that's present in the crop that's fed to them. Then we again have, particularly with manure management, losses of various gases and liquid forms, dissolvable forms into the environment. So at the end of the day, according to this particular study, and the numbers vary, and these are broad brush averages, that for 100 units that we put into the crop production system on the left, only about, if you're a vegetarian, you're consuming vegetable products, only about 14 of those original units of nitrogen are consumed in the food that we eat. If you're eating animal products, meat and dairy, only about 4 out of those 100 units are being consumed on average. Now, it varies a lot. Chickens are different than beef, it's different than dairy, but that's a global average. So it's a very linear, inefficient, and leaky system. It's produced a lot of food and it makes us better nourished than at any time, but also because it's so leaky, it is causing severe environmental problems. Next slide, please. So now let's focus on the main topic here, which is nitrous oxide. This is a graphic showing back 2,000 years of nitrous oxide concentrations in the atmosphere. Obviously, no one was around measuring that 2,000 years ago, but we can extract, not we, I don't, but scientists have extracted bubbles from ice cores in Greenland and in Antarctica and can measure the nitrous oxide and therefore project backwards what the concentration was. And as you can see, it was relatively stable at about 270 parts per billion throughout most of that period up until the Industrial Revolution. And then in the 19th century, it began going up, partly because of use of fossil fuels, but also because agriculture was expanding, because human populations were expanding and demanding more food. And the more food we produce, the more of that nitrogen we liberate. Red dots are that record of measurements in modern time, and you can see how quickly it's going up. It's now going up at the rate of about 3 parts per billion per year. So it is, as I said before, the most important ozone depleting substance, the third most important greenhouse gas after CO2 and methane. Now, I'm the third child in my family, and I became aware of the fact that number 3 needs to have an advocate, right? So nitrous oxide is sometimes referred to as the forgotten greenhouse gas. It is contributing roughly 6 or 8% of radiative forcing, in addition to its effect on the stratospheric ozone. But it's also very long-lived. So what its mean residence time in the atmosphere is over 100 years. So what we are doing today will affect several generations into the future. And it is strongly linked to food production. So we can imagine decarbonizing our society. We can imagine running our automobiles and even our airplanes maybe someday on some form of fuel other than fossil fuels. But we're always going to need nitrogen to produce food. There's no way around that. We have to have it. And so this is going to be a particularly difficult challenge going forward in figuring out how we can continue to provide nourishment to 8, 10, perhaps more billion people without increasing that burden of nitrous oxide in the atmosphere further. And most of the nitrous oxide is coming from the agricultural sector. I'll show you some other sectors in a bit, but most of it comes from agriculture. Next slide, please. This is a bit of a busy graphic, so I'll walk you through it. And the most important part, it's showing the main sources, both natural sources and anthropogenic or human-caused sources of nitrous oxide. At the very top, you can see that the anthropogenic sources add up to, in this case, somewhere around 6.5 teragrams per year of nitrogen as N2O. There are natural sources because nitrogen cycles in forests and in the ocean, and there is a little bit of leakage out of that as well. It's not as much as in agriculture in terms of amount per hectare, but we have a lot of, the globe is full of oceans, covered with ocean, and we have a lot of forest yet. And so there are natural sources, and that's shown by the big green arrow, the thick green arrow, which is roughly another 6 teragrams or so. And you can see also in the oceans, another 3.5 teragrams or so. Before the Industrial Revolution, those natural sources were in balance with the natural sink, which is the blue arrow on the right, showing that there is destruction of N2O in the stratosphere. And if the source and the sink are roughly in equilibrium, then the concentration in the atmosphere stays stable. But what's happened since the Industrial Revolution and since the tremendous growth of human population and food production, all these sources on the left have become increasingly important. So now the budget is out of balance. There's more source than there is destruction in the atmosphere. And so the amount in the atmosphere grows, which is the amount of in the middle there, which is roughly 4.6 teragrams per year, which translates to something like 3 parts per billion in the atmosphere. Next slide, please. And there are regional differences in terms of where this nitrous oxide is coming from. So this shows the sum of anthropogenic N2O emissions from all sectors, but it's predominantly agriculture, for various regions of the world. If you look back in 1980, Europe was the most important source, followed by North America. So as with other greenhouse gases, it's mostly the global north that has the long-term burden of having contributed most over time. But more recently, since really the 21st century, you can see that East Asia has overtaken in terms of the largest source. And you can also see that Africa, South Asia, South America are also increasing sources. So this is a global phenomenon. So even in Africa, where the cost of fertilizers is prohibitively expensive, there is increased food production and there is increased nitrous oxide production. Next slide, please. So as part of this global assessment that we referred to earlier, this is an assessment that was done under the auspices of the United Nations Environment Program. They have a branch that's called the Climate and Clean Air Coalition. They've studied the major greenhouse gases and what they call superpollutants, including methane. This time they focused on nitrous oxide, and I was honored to be a lead author in one of the chapters, and this comes from that work. This shows the current estimates, or 2020 estimates, is in the left-hand column, and then 3 scenarios going into the future. A reference scenario, which is sort of business as usual, and emissions predicted or estimated, projected, I guess is the right word, for 2050. And then 2 other scenarios. The next one is a technical reduction scenario. So no changes in our lifestyle really, but implementation of technologies that we think could reduce nitrous oxide emissions. And the one on the far right is both the technological and societal change, and that really is referring mostly to dietary changes, mostly from the high-income countries to consume less meat and dairy. Let's see. Can you try advancing once? I mean, I don't quite remember what my next one is, if it's next slide, or just try advancing once. I might have you go back. Yeah, I thought there was an animation here. So what this shows is that without abatement, if we go that second column from the left, the reference scenario for 2050, without abatement, we would expect emissions to grow about 30% over 2020 levels to 2050. But there are mitigation options available. So it's like, what I like to say about climate change in general is that we really have 3 options. We're talking about CO2, methane, or N2O. And there's going to be some combination of all of them. There is going to be some suffering. It's already happening. There are people who are suffering the consequences of climate change, of storms, of droughts, and so on. There's adaptation, the things we can do to try to adapt to the climate to make our agricultural systems retain their productivity. It's expensive in many cases, you know, or make our communities more livable. It requires better management of water, maybe some more air conditioning. That's adaptation, and it's expensive. And the third thing we can do is to mitigate or abate emissions, reduce our emissions. And the sooner that we adapt, the less suffering there will be. And the sooner that we abate, the less need there will be for adaptation. So, and we know in many cases what we need to do to mitigate. Even with nitrous oxide, which is directly related to food production, we have a number of ways that we can at least partially abate those emissions. And these are two of those examples. We'll move through these and show which are most likely and at what cost. But I've shown here adipic and nitric acid. That's an industrial process. Adipic acid is used in making nylon. And not only do we use nylon for our clothing, but a lot of cables that are used, for instance, the average automobile has a tremendous amount of nylon in it. It surprised me. And nitric acid is used for munitions and also for fertilizer production. There's livestock and manure, managing croplands and grasslands, wastewater treatment, and then the total, and there are a few other minor ones. So now let's move on to the next slide, please. So as we think about what we can do in the agricultural sector in particular, since that is the largest sector, in many parts of the world, and you may have heard it here, the approach has been sort of an incremental approach of improving our knowledge of how nitrogen fertilizers are used. And this has been referred to as the 4 R's. Using the right source of fertilizer, the right type, at the right rate, applying it at the right time, and in the right place. And so I have, and this circle here is showing the various environmental, economic, and social impacts that we think about as we apply the 4 R's. Now I have a series of 4 animations that we'll go through one by one. If you'd advance to the next animation, please. So, right source, slow release fertilizer is one, so that when the fertilizer is applied, it doesn't all go into the groundwater at once. It is gradually released to try to make the release in synchrony with when the crop needs it. In the India context, that would be neem-coated fertilizer. In other parts of the world, there are other kinds of slow release of fertilizers. Nitrification inhibitors are not used so much here, although they might be in the future someday. But certainly balanced nutrients is extremely important. NPK and also micronutrients and sulfur. You can waste a lot of nitrogen if you're low on some of the other nutrients. The second one is rate. Well, soil testing, I understand, has grown a lot here in India and in many other places in the world. There are online tools to help farmers. There are crop sensors that can be used to determine when a particular crop is deficient in one nutrient or another, including nitrogen. The timing, spring versus fall, that applies more to temperate climates, but even in tropical climates, timing in terms of when the crop is going into production. It may be wet season, dry season. Timing when at various stages of the crop when it needs the nitrogen or other nutrients the most. So side dressing refers to, instead of putting all the nitrogen in one big bolus at the beginning of the cropping system, applying small amounts at various times. I just visited a bunch of farms in Maharashtra where drip irrigation is being used, and fertigation, applying small amounts of fertilizer with the irrigation water is being used, and that would be sort of spoon feeding the crop small amounts of nutrients as the crop grows. And finally, the placement of where that fertilizer. So we have a lot of experience The problem is trying to figure out how to make these recommendations to farmers in ways that farmers will adopt and that farmers can afford. And that's a large part of the challenge, the socioeconomic issues. We have a lot of technical knowledge, the socioeconomic considerations of what works for farmers, who they trust, where they get their information, why they would adopt some of these practices are some of our biggest challenges. Next slide, please. And this applies to the various forms of nitrogen pollution. The second from the left graphic there is nitrous oxide. This is from a meta-analysis by a Chinese scientist showing that, well, EEF on the top there is enhanced efficiency fertilizer, such as the neem-coated or the slow release and the inhibitors. And then the various 4 R's, rate, type, time, place, using more legumes in the crop rotation and so forth. And all those points to the left of the line, the ones that are in red are statistically, well, no, all the points to the left of the line are ones that we know would reduce emissions if they were adopted. And this is according to a large meta-analysis across the world. But note that some of the same things that reduce nitrous oxide emissions also reduce ammonia emissions, also reduce NOx emissions, also reduce nitrogen leaching and runoff. And some of them improve yield. So there's the possibility of a win-win situation here of improving yield while a win-win-win-win-win situation, improving yield while reducing many different forms of nitrogen pollution. Next slide, please. So this is where it gets complicated, and this is a diagram from the N2O assessment. In the N2O assessment, we realize we can't just look at N2O in isolation. We have to look at it combined with the other, well, with other nutrients, yes, but also the other forms of nitrogen pollution. So you can see in the far left, the diagram showing that from the soils, there is, and from agriculture in general, and also from industry, there's emissions of nitrous oxide, ammonia, and NOx, NOx. That is, the NOx is a precursor to tropospheric ozone formation. I already mentioned that. And ammonium and nitrate form aerosol particles in the atmosphere, which produces PM 2.5. And some of those are rained down back onto the land and onto water surfaces. And so there's a lot of things going on here that are interacting together. Various kinds of pollution. We also relate it to carbon dioxide uptake by the forest, depending on how much nitrogen they have. Indirect emissions, when the nitrogen goes downwind or downslope to other sorts of ecosystems, forests and wetlands may emit N2O. But what we found in this assessment, and if you'd advance this to the next animation, please, is that by improving our nitrogen management, we can reduce PM 2.5, which we need to do for human health. I mean, it's a very serious human health problem. There are millions of people who die globally from respiratory disease from exposure to PM 2.5. You may not have heard of it. Oh, uncle or aunt died of PM 2.5. No, they died of a respiratory disease. But PM 2.5 probably contributed significantly to it. So we need to clean up the air. But it turns out that those particles, those fine particles, are reflecting back the sun's radiation. So those particles are actually having a cooling effect. So as we improve nitrogen management and reduce nitrous oxide emissions, we are also reducing, and that would reduce the warming effect of N2O, but we're also reducing the PM 2.5, which has, the PM 2.5 has a cooling effect. So by reducing it, that has a warming effect. So the two can cancel each other out for the next few decades. Eventually, the N2O effect will take precedent, will become more important. And remember, I said nitrous oxide has a very long lifetime in the atmosphere of over 100 years. So towards the second half of the 21st century, and many of you will still be alive in the second half of the 21st century, and your children and grandchildren, the N2O will become more important from a radiative forcing point of view than the PM 2.5. But in the meantime, we need to do both, because we need to reduce the PM 2.5 for human health, and we need to start reducing the N2O for the sake of the climate and the stratospheric ozone. And these benefits that will be reaped vary depending on the region of the world and the country. This is an estimate. The below the line estimates are the savings from fertilizers by using fertilizers more effectively. That saves the farmer the cost of the fertilizer. The red box below the line is the net effect, because implementing some of those fertilizer reduction technologies will have costs themselves. So that shows the net effect, which is fairly modest, but important nevertheless. The benefits above the line of the various colors are monetization of benefits like human health. So how much is a human life worth in terms of monetary value? How much is avoiding respiratory disease worth? And you can see that the health benefits are greatest in countries like China and India. The climate benefit relative to the health benefits and ecosystem benefits is actually quite small. The ecosystem and then the yield benefit is quite large in some places like sub-Saharan Africa, where actually this could mean increased yield by making fertilizers more available and more effectively used. So it really varies by region in terms of what the impacts would be of adopting these scenarios of improved nitrogen use efficiency, those technological and social scenarios. Next graphic, please. So I mentioned that there's several sectors in which nitrous oxide could be reduced. The industry sector does not have a large amount of abatement potential, but it could be done almost immediately because there are cost-effective technologies that could be implemented now, and they are being implemented, but the cost isn't zero. But in terms of cost relative to other greenhouse gas abatements, it's very cost effective. And so there's been some carbon trading and nitrogen trading schemes used to try to promote adoption of those technologies in the industry sector. Next slide, please. The bigger challenge is the large emissions from the agricultural sectors. And those costs vary quite widely in terms of costs of that column that says range of abatement costs in terms of dollars per ton of nitrous oxide or dollars per ton of CO2 equivalent. As I said, nitrous oxide is about 270 times more potent than CO2, so you can convert that to a CO2 equivalence in terms of cost. And you can see that some of the costs in agriculture at present with present technology are really very expensive. Some are not so expensive. And we need to develop those technologies to bring the costs down. We know that they work, but we've got to be able to bring the costs down in order for farmers to adopt them. Next slide, please. So as we think of this global cycle, I already mentioned to you once before that most of our crops go to feeding our livestock. And you can see that arrow with the number 85 towards the center, showing most of our crops are going to livestock. And then all the red arrows are showing the ways that nitrogen leaches out to the environment or goes out in various gaseous forms. What are some of the more disruptive, more profound interventions into this system that we could do besides just the 4 R's, besides those incremental approaches that I talked about with the right rate, right time, right place, and so on? Well, let's advance to the next animation. One is that those 4 Rs and various approaches that we can take within the croplands, including crop breeding, a number of people working on breeding crops that have higher nitrogen use efficiency. That's one approach. Next, another possibility is trying to get more nitrogen directly into the animal feed instead of depending entirely upon growing crops to produce crude protein to feed to our animals. There are technologies available. In fact, one that I discovered here in India, a startup company that is using something called green ammonia that we could talk about more. I don't have time to talk about it now, to produce microbial or to produce fungal protein that they then turn into a flour and add it to chapatis for human consumption. And some of it goes to animal production as well. So there are other ways of getting protein directly to the animals rather than through this leaky pipe of growing crops. We'll still need crops to feed the animals, but there are technologies to reduce the amount of dependence on crops for our livestock sector. Next. And finally, in virtually almost every country throughout the world, there are very poor rates of manure recycling. This is largely due to this separation of crop and animal production system in many countries, not only high income countries, but middle income countries as well. I believe both India and the United States, there are estimates that maybe about 20% of animal manure is recycled on the croplands. And that's a big challenge technologically and socially as well, but there are solutions for improving that. So I want to leave you with this last diagram that gives you sort of that vision of the future of what we call nitrogen 2.0. If nitrogen 0.0 was our dependence on manure and bird guano and some other miscellaneous night soil, human waste prior to the Industrial Revolution. Since the Industrial Revolution, nitrogen 1.0 is our dependence on Haber-Bosch, which has produced a lot of food, but as you can see on the top, it's a very linear system with very large losses into the environment. Imagining a new system that we call nitrogen 2.0 that is more circular, more targeted, and more efficient. And it has, as I said, trying to skip a trophic level by feeding more nitrogen directly to a livestock rather than depending entirely on crops. Crop breeding and management innovation to reduce nitrogen use within agricultural fields and increasing the rates of recycling of manures. And this is would be a vision that maybe towards 2050, but we need to start working on it now because these technologies take years or decades to develop and to have adopted. This would get us beyond those modest reductions in nitrous oxide, could eventually get us to the point that we have an agricultural system that is still dependent on nitrogen as it will always be, but a system that can use that nitrogen more effectively, more targeted, in a more circular way that we can truly call it a more sustainable nitrogen. So with that, I thank you for your attention and thank you for this invitation to speak here today. And I look forward to talking to many of you throughout the rest of the day. Thank you. Want to say something?
Pradhaman sir, you have something to say? Okay, ma'am.
Thank you, Dr. Davidson. That was like a very important for agriculture sector. we are always talking about the CO2 emissions with less emphasis on nitrous oxide emissions. I was just wondering, like, why Europe, the anthropogenic emissions of nitrous oxide in Europe is declining? What can be the reasons? That's my one question. One more is there. Europe, yeah, your graph shows that it is declining in Europe, whereas Asia and Africa, it is increasing. Pardon me, I have one more question. Can I ask it now, or you want to answer this?
Why don't I answer that one first?
Yeah.
So there are two major reasons. Europe has effectively eliminated all of the industrial emissions of nitrous oxide. So that's a small contribution relative to agriculture, but it's one that Europe has been ahead of everyone else, including the United States and China, in reducing industrial emissions. Second, the Europeans realized in the late 20th century that they had a very large nitrogen pollution problem. Mostly they were worried about their groundwater, and their river water had high nitrates. And so they had what they called the nitrates policy, nitrates initiative or something like that, in the 1990s that regulated how much fertilizer nitrogen farmers could use. And as a result, the efficiency of their nitrogen use increased tremendously, and while their productivity was still also increasing because of improved varieties of crops and things like that. And as a consequence, as a side benefit, nitrous oxide also decreased. So the production of nitrous oxide, also the leaching of nitrate, is a very nonlinear process, so that for most of your additions of reasonable amounts of nitrogen fertilizer, say up to 100 kgs per hectare, you get very low rates of nitrous oxide and nitrate leaching. But once you get up to 150, 200, or even 300 kgs per hectare, it's very nonlinear in that the fraction that goes off as nitrous oxide increases. So that's why convincing farmers to reduce from, say, 200 kgs per hectare to 180 or 170 could have a big impact, even though it's a relatively small reduction in fertilizer, because it's that additional amount that is in excess that gets converted to these various forms of pollution. And that's what happened in Europe, is that they got rid of some of that excess amount, and that helped reduce those various forms of pollution.
Thank you. And another one is a clarificatory question as to, when we talk about nitrous oxide emissions from fertilizers, from agriculture sector, does that include the emission during the production of the fertilizer and transportation?
Well, when I'm talking about nitrous oxide, it would not include that. The production of the fertilizer involves very significant CO2 emissions. So roughly, I think it's about 2% of anthropogenic CO2 emissions, or the radiative forcing from it, can be attributed to the production of the fertilizer. And then the transport adds maybe another 1/10 or 0.2%. So it's a very important source of CO2. When I was talking about the contribution of agriculture to the N2O budget, I was not including that CO2. There are new technologies called green ammonia that are being developed. The possibility of producing ammonia fertilizer and ammonia as a shipping fuel, marine shipping fuel, using renewable technology. And that's actually one of the things that I'm studying while I'm here in India, is that India is one of the leaders in this development of the technology of green ammonia.
Thank you. Thank you very much.
Thank you, Dr. Davidson, for that wonderful presentation. This is probably a very, very important topic as far as our state is concerned. We are looking at mostly bringing our agriculture sector carbon neutral. We are taking so much of efforts to reduce the emissions, but mostly confined to methane, right? But we know the real fact that much more than methane, there is the nitrous oxide is playing a crucial role. Since heavy application of nitrogenous fertilizers, especially, I think 70% of the nitrogen fertilizers is exclusively one, that is urea, right? And the nitrogen use efficiency has been estimated to be even to go as low as 30% in Kerala conditions. So it's a very, very serious, and the use of the manifold increase in the use of urea has been observed during the recent times. Maybe after the great flood in Kerala in 2018, the soil health has drastically declined, and people's dependence on urea has been manifested to be manifold increase. So this context gives us probably your presentation has a lot of relevance in this context as far as our state is concerned. My first question is, you said about the impact of nitrogenous or the so-called nitrous oxide on forest vegetation dynamics. You said that is some of the increase in the non-native species, and the native species may go down, and there could be a proliferation in what is that mechanism actually happening? How the non-native species showing more dominance?
But it happens first for the understory species. So this was very well documented in Europe, which had very high rates of nitrogen deposition. So countries like the Netherlands, they have a lot of animal production and hence a lot of ammonia emissions from animal manure. And it goes a little bit east to the forests of Germany, and it is deposited on those forests at very high rates, greater than 30 kgs per hectare per year, which is a lot for a forest, particularly a temperate forest. And so the native species are not adapted to be able to use that nitrogen. They are slow growing species. But weeds or invasive species tend to be species that are fast growing and can utilize a resource like that very rapidly. And so a lot of invasive non-native species are favored by the availability of this new resource of more nitrogen in the soil. Whereas the native species, which have evolved relatively slow growing rates, are not able to quickly absorb that nitrogen and grow. And so they get outcompeted by those invasive species. Now, to what extent that, I don't know if your nitrogen deposition, how high it is here in India and whether that is having an impact. I would think with all the PM 2.5, you must have some pretty high nitrogen deposition somewhere. But I don't know how that's played out here.
Maybe because it's very important. These kinds of situations are happening to a larger extent in tropics. The forest physiognomy is changing, the forest health is changing. For example, in Kerala, invasives are coming in a big way, and the natural forest ecosystem, the dynamics is changing. Maybe, as you rightly said, there could be an interplay of this factor as well in deciding this.
That could be.
Yeah, but I don't have, I have, as of now, I have not come across with any such studies from topics in this slide. Well, I have already mentioned, if you look at the Indian scenario, there is single most villain is urea. Is there a real substitute? Or you said about many measures. We are following measures like, there are some substitutes like diammonium phosphate. There are some, but the efficiency with which urea provides you nitrate, ammonia, there is no other substitute as compared to the urea. That's a non-factor. But still, we have to reduce the impact. There are some suggestions like neem coating, pelleted urea application, or in paddy field, probably there is a strategy like you go for a deeper placement of the fertilizer rather than the broadcasting. You go for drilling and what is your take on this kind of strategies? How far that can reduce the emissions?
Well, of course, that's going to be regionally specific in terms of the soil type and how feasible that is. Also, the type of agricultural equipment that's available and what's affordable by the farmers. Where it has been used, I think the deep drilling has been effective, particularly for urea or for anhydrous ammonia. If you don't get it down deep, a lot of it goes off as ammonia near the surface, especially if the soils are circumneutral or slightly alkaline, then a lot of it is converted to ammonia gas and it's lost. But if you put it down deeper, you won't lose as much ammonia gas. However, there's a trade-off. If you put it deeper, you end up getting more nitrous oxide because the soil is less well aerated. And the main source of the nitrous oxide are denitrifying bacteria that do their denitrification where there's less oxygen. So there are some cases where there are trade-offs. I said in general, most interventions will help us with all forms of nitrogen pollution, but there are some exceptions where you could increase one form versus another. Same's true with alternative wetting and drying for rice paddy. You may decrease methane, but you might increase N2O if the alternative wetting and drying is not done properly. So that's the job of all of us and this generation of scientists that we're training to figure out how to do those things right so that we don't have unintended consequences.
Okay, my last.
I would just say that regarding urea, yes, there are alternatives. But part of the problem with urea, at least here that I understand that from the colleagues, Indian colleagues that I've spoken to are experts in this field, is that because the price is so low, that it always seems like more is better. And even you said urea is the most efficient or most effective. Well, there's a point where adding more is not efficient or adding more is not effective. You get to a plateau on a curve, a dose versus response, it plateaus out. And because urea is so inexpensive, because it's so heavily subsidized, most farmers are well out on that plateau and they could pull back 10, 20, even more percent and still not experience significant risk of crop loss. So even if urea is continued, there are policy options. They might be politically difficult, but there are policy options to reduce emissions from urea. Also, the synthesis of the urea, although it's mostly domestic, over 80% of the fertilizer is produced within India, but it depends upon imported fossil fuels. So even though you're producing your fertilizers domestically, you are still vulnerable to geopolitical events such as the war in the Ukraine that affects the cost of fossil fuels, which is going to affect the ability to synthesize the fertilizers that you need for your food security. So finding alternatives to that kind of production would be advantageous. And I don't know whether green ammonia, using it, synthesizing it with renewable resources, which India has in abundance, whether that will work or not. That's kind of a visionary future. I'm sorry I interrupted you from your other.
No. Absolutely. So my last question is like you said about synthetic amino acids inclusion of more of synthetic amino acids in the dietary components of animals, What is its applicability from an Indian perspective? Because is it too costly an affair, or rather can it be included? Because vast majority of Indian farmers, they're all having subsistence farmers.
Right.
So is it possible for them to, or is it a too costly kind of affair for them to manage, to increase more of synthetic amino acids so that?
Right. Well, before I came here, I would have answered to you, yes, I'm sorry, that's mostly a high-income country perspective. High-income countries might have the capacity of producing synthetic amino acids through a fermentation process and so on. But actually, after I got here and learned from speaking to some startup companies that are beginning to work on this, there are actually some applications here in India that make a lot of sense, that are more specific to the India situation than, say, the North America or Europe situation. For instance, there's a startup company in the Delhi area called Acme they are in the business of producing green ammonia, both small scale and large scale. So using renewable energy to split water into hydrogen and nitrogen, hydrogen and oxygen, using that hydrogen, which is green hydrogen, to synthesize ammonia fertilizers and ammonia fuels. They are then experimenting with using that to grow fungal biomass in a reactor, in a fermenter, adding ammonia to it. So they're not making synthetic amino acids, they're growing microbial biomass or fungal biomass. And then their business model is to try to convince the government that they can take that fungal biomass, make a flour, use it to enrich food, enrichment of chapatis or what other kind of food it might be appropriate for. And they've done taste testing to determine that it doesn't negatively affect the taste. And if the government would be willing to subsidize the additional cost of enriching, fortifying the flour that's used to make those foods, then this is a means of getting more of that protein directly into human and animal diets, rather than through the leaky pipes that I showed you of depending entirely on crops. So we're still going to need crops. We're not going to get rid of them, but we're talking about perhaps increasing the percentage somewhat of that's fed directly to humans or to livestock. So that the same company, they said about 70% of the mycoprotein that they talk about, the protein from fungi, they say about 70% of it can be used for human consumption and 30% for animal consumption. And they're just experimenting right now with using this green ammonia plus corn extract, corn syrup extract. But they said that other companies are looking at sugarcane, even food waste like potato peels as the source of the carbohydrate to go into the fermentation reactor. So there's a lot of innovation happening. And actually, I think India is very well positioned to lead that innovation in ways that I don't think anybody in North America is looking at growing fungal biomass to feed to put in the human or livestock food production system. So that's very innovative and perhaps appropriate. That we would not be able to convince the American government to subsidize fortification of flour to make bread. They subsidize the production of biofuels, but they wouldn't subsidize it. But it's entirely possible, as I understand, you know more about it than me, that there could possibly be subsidies for fortifying foods consumed by a large fraction of the population, if the scientific basis and socioeconomic basis for it could be made.
Thank you very much for the clarifications.
Hello, sir.
Couple of questions from the students
Hello, sir. Am I audible?
from online.
Yes, sir. Yes, sir.
We can hear you.
Hello, am I audible? Hello, am I audible, sir?
Yes, ma'am.
Yes. Good afternoon, sir. I am Dr. Varsha from D.Y. Patil Agricultural and Technical University, Tasande, Maharashtra. From Dr. K. Prithapan, sir, is our Honorable Vice Chancellor. Because of meeting, another meeting, he is busy with the same. Actually, COVID, your session was very informative and enlightening us. So I am the researcher from computer science and engineering background. So I would like to ask one question regarding the aerobic digester, like biogas digester we are using. So how it will be help for the NO2 or nitrogen emission reduction? And second question is, what are the opportunities for the AI and IoT for the implementation?
Okay, the first question, was it anaerobic digestion for anaerobic digesters of manure? Is that was, and what potential does that have? Is that the question? Do I understand correctly? Okay.
Yes, sir.
Yes, this is a very interesting topic. I don't claim to be an expert on that particular technology, but I've the colleagues with who experts with who I have spoken have explained to me that this is there's certainly a great deal of potential for just so make everyone understands what we're talking about. One of the ways of recycling manure is to put it into a digester under low oxygen conditions. And in the process, it can produce methane gas, natural gas that can be used as a fuel, that can be captured and used as a fuel. And also there's a residue that no longer has the bad odor that manure and urine usually has. And so this residue is also easier to handle and could then be recycled back onto croplands. So there's a double benefit here. You're getting rid of a manure waste that sometimes they don't know how to get rid of it. You're producing a fuel, methane, that can be used on the farm or for other places. And you're producing a residual that is easier to transport and apply onto croplands. One of the problems with applying manure onto croplands is that here in India, I imagine, where you have small plot sizes and you still have, in many parts of the country, the livestock integrated in the landscape to some extent. In the US, it's totally disaggregated. And the problem of the manure is too heavy, too wet to be able to transport economically to the production where the crops are. So if you can take the water out, which anaerobic digesters do, it makes it a material that's much easier to ship longer distances and to use and to apply to croplands. The question is how to do this economically and how to bring it to scale. It's been demonstrated at small scales, medium scales, but how to bring it to scale is the challenge of that technology. I don't know if I answered your question, but could you repeat the second question, please?
Yes, sir. Yes, sir. My second question is related with the how we can means what are the opportunities of artificial intelligence and IoT for reduction of such a nitrogen emission.
Question is how to use artificial intelligence.
Yeah. Yes.
That's so That's an excellent question. Of course, artificial intelligence could help us with such things as engineering how the best way to make synthetic amino acids, for example. I would think that would be an engineering question that artificial intelligence could help with. Another one that I could think of is the one of the ideas that some of my American colleagues are using for manure management is what they call manure sheds. You know, we've all heard of watersheds and air sheds, but a manure shed is the area over which livestock are producing manure and the area over which it could be used as a product in croplands. And it's kind of complex to figure that out in terms of you need to have a lot of data on where the croplands are, where the animal production system is, what transport is available at what cost. And so there are various layers of data and various connectivities that need to be included. And that just comes to mind as one example of where perhaps artificial intelligence could help us sort that complex thing out. And I'm sure, you know, more smart people putting their minds together on this would come up with a lot of other examples.
Thank you so much, David Ji, sir,
Thank you.
for excellent guidance. Definitely we'll work on this problem statement and so that we can help the sustainable agriculture. Thank you. Thank you so much.
I think there was one more question here in front if we have time.
Since nitrous oxide is having high lifetime and high global warming potential, which is the best way to capture or store nitrous oxide from atmosphere?
Which is the best way to do what?
Capture or store.
Capture the N2O? There really are not any viable technologies now to be able to pull N2O out of the atmosphere. As in carbon capture and storage, if that's what you're thinking about, or even methane removal from the atmosphere. There's some interesting research for that now, but there are no technologies that I'm aware of that could remove the N2O from the atmosphere at a scale and for an economic value. It's better to avoid the emission rather than try to remove it once it's already in the atmosphere. Now, there is removal naturally up in the stratosphere, but I'm not aware of any ways that we could geoengineer a process to enhance the rate of nitrous oxide removal in the stratosphere. Is that the question you were asking me? Okay, thank you.
Sir.
There's another question back there. Yeah. I'm delighted that there's more questions. Thank you for staying so long.
Good afternoon,
spoke a long
sir.
time. Yes.
I am Aranya Ji. I'm an environmental science student. So my question is, how can sustainable nitrogen management practice be developed based on the result of a comprehensive nitrogen budget? So,
How can sustainable nitrogen practices be developed based on the nitrogen budget that we talked about? Okay. Well, that's a great question. And in fact, I just got through touring some farms in the state of Maharashtra, where there is a group working with farmers on their nitrogen budget. So what we mean by nitrogen budget is, you know, all of your inputs, you know how much fertilizer you're applying, you know how much manure you're applying, you have a rough, at least a reasonable approximation of the nitrogen concentration. So you know how much nitrogen is going into the pipe, so to speak, that metaphor of the pipe. And you know how much harvest you have because you sell it. You know how much you sold. And each crop has a typical nitrogen concentration. So you know the output. So now you can take your input minus your output, and that's your balance, or that's the amount that is either staying in the soil or it's going off into the atmosphere somewhere. And unfortunately, not much of it stays in the soil. And so it's either going off as a gas or going as nitrate into the groundwater. So what this organization is doing is that they're collecting those data and they're comparing it to region-wide data on, and also results from agricultural universities like this one, where there are recommendations of what the application rate should be. And where this nitrogen balance is high, in other words, the inputs are much larger than the outputs, they're suggesting to the farmer to gradually cut back a little bit. They're not making major drastic reduction suggestions for reductions, because they want to get the farmer's confidence first, and suggesting that the farmer might reduce their application by 20 kgs per hectare. That's not a big amount. And then if they can, and only do it on 1 hectare or 1 acre, and see what the results are like. And then if they get the farmer's confidence that, wow, they got just as good a yield on that 1 acre with using 20 kgs less, maybe next time they can go down a full bag, 45 kgs, you know? And that's a way of using the actual data from the farmer, what they used, what they produced, and keeping track of it over time to help the farmer see that, yes, you can reduce your application of urea because it's been over-applied in the past. And some of them actually then comment about how they see some improved soil properties, or they see, in some cases, they may actually have some improved crop productivity if they're reducing some over-application. So I think actually everywhere in the world, the research has to include the farmer, and has to get the farmer to not just, you know, receive advice from up high saying this is what you should do, but engage them in the research at some level. It'll show them the numbers and get their knowledge as to their input as well. And I think that's the way that this nitrogen balance can help lead us to a more sustainable type of agriculture. Thank you
sir.
for your question. Okay, last question.
So from the time of industrialization, there has been a rise in fossil fuels, which has become a major contributor to the reactive nitrogen in the atmosphere. But while we replace the emissions by the emission of fossil fuels by converting by using alternatives such as EV or electric vehicles or electric powered motors, but during the production of lithium-ion batteries, nitrogen is playing a part in every process during the process of the production of lithium-ion batteries. So do you think at the end of the day, we are replacing the emissions by fossil fuels, or maybe worse, even increasing the amount?
Well, that's a good question. And it's important for any type of intervention to try to do a life cycle analysis. To the extent that you have data and capability to do it, it's always wise to do a life cycle analysis. Excuse me. To give you a good example, in the United States, there is a very heavy subsidy for producing maize-based ethanol. And that's presumably to replace fossil fuels. Well, it does replace fossil fuels to some extent. And so it's supposed to reduce greenhouse gas emissions. Well, it does reduce carbon dioxide emissions from combusting fossil fuels in our automobiles. But in order to grow the maize to produce the ethanol, what do you have to do? You have to add a lot of nitrogen fertilizer. And synthesizing the nitrogen fertilizer also produces CO2. And applying the nitrogen fertilizer on the maize field produces nitrous oxide. So you have to do a full life cycle analysis to know if this subsidy for biofuels from, in this case, maize, actually gives you a net benefit for greenhouse gas emissions. And it's been debated as to whether it is or not. Brazil had to do the same when they developed sugarcane for producing an ethanol fuel. And now we're talking about so-called sustainable aviation fuel, right? I put it in quotation marks because I'm not sure if it's sustainable. Yes, we need to decarbonize our aviation sector, but whether we can really do it by growing crops, if the crops have to be fertilized with nitrogen, I'm not sure how sustainable it is. We have to do life cycle analysis. Now, I don't know if you were thinking of other things like producing EV batteries or wind turbines or solar panels. My impression is that in the case, that all of those have some carbon embedded in them, some carbon dioxide emissions that are emitted in order to produce those things. But I think in those cases, the life cycle analyses have already been done to show that the net benefit over a course of the lifetime of that renewable source of energy far exceeds the the benefit is greater than the CO2 emissions that would have occurred had you continued to burn fossil fuels. So it really depends on the type of intervention that you're trying to use to reduce the greenhouse gas emissions. But it's a very good question, and it's something that we need to pay close attention to for each of these interventions. Thank you so much. Great questions. I really enjoyed it. Oh, there's one more. Sure. Compared to organic farming? Oh, how much time do we have? This is a complicated question. So denitrifying bacteria, nitrifying bacteria, the ones that produce N2O, they don't really care whether the nitrogen is coming from an organic source or an inorganic source. The real importance is how available is nitrogen relative to carbon, and is it in excess so that the nitrifying and the denitrifying bacteria can use the nitrogen and produce the N2O. So there are places in the world, and I can think of a place in eastern Pennsylvania where descendants from Germany that we call the Amish use entirely organic agriculture. They also don't use modern, they don't use tractors and things. They use a sort of a 19th century technology almost, but they use a lot of manure. And they are one of the biggest sources of nitrogen pollution to the Chesapeake Bay because they use a lot of manure. So simply because it's organic doesn't mean that it's going to be benign. That said, there are a lot of things that we can learn from organic agriculture. Personally, I prefer the term regenerative agriculture because it uses some basic concepts like keep the soil covered at all times. Try to integrate animal and crop production. Don't overuse fertilizers or pesticides. Use traditional knowledge when you can. Use integrated pest management when you can, and revert to herbicides and pesticides only if you have to because the other methods don't work. Use stubble management, use green manures, use compost to the extent possible, but don't eliminate the possibility that you may also need to use some fertilizers at appropriate times, lime at appropriate times, perhaps some judicious use of herbicides and pesticides. So my concern with strictly organic is that there are times when not everything is ideal. And if we try to sell that to farmers and then there's an insect outbreak that can't be controlled, then we lose the farmer's confidence. Now, Some places there's a niche market for the organic produce. And if there's a niche market and the farmer has the resources to be able to apply all organic methods to supply that niche market, great. And if, as you and I, as consumers, if we want to buy organically grown produce because we don't want to have pesticide residues, that's great. But I don't think we're going to feed 8 to 10 billion people using entirely organic agricultural approaches. If we did, I think we would have to cut down the rest of the tropical forests in order to have enough cropland to grow all that food. I think we need some form of intensive agriculture. It doesn't have to be as reliant on fertilizers and pesticides and herbicides as we currently rely upon. We can pull back on those. But I think we need all of the tools in the toolbox in order to have a food production system that will continue to nourish 8 going on 10 billion people. That's my personal opinion. So I want to emphasize that whenever a scientist gives an opinion like this, that is partly based on the science, but it's also based on personal opinion, that you should express that opinion. And other people may have different opinions, and I can accept that. We can discuss it and debate it. But that's my personal answer to your question. Thank you.
Thank you, sir, for your thought-provoking lecture that has deepened our understanding of environmental sustainability and agricultural management.
To express our heartfelt gratitude, I now invite Dr. P.O. Namir to present a memento to Professor Eric A. Davidson as a token of our appreciation.
To formally conclude the session, I invite Ms. Shahida P.A., Assistant Professor, Department of Environmental Science, to deliver the vote of thanks.
A warm good afternoon to everyone. It's truly a privilege to stand before you and deliver the vote of thanks for today's enlightening seminar on how agricultural management affects emissions of nitrous oxide, the nearly forgotten greenhouse gas. On behalf of the College of Climate Change and Environmental Science, Kerala Agricultural University, I would like to extend my heartfelt thanks to all of you for joining us today on this insightful seminar. First and foremost, I would like to express my sincere gratitude to our esteemed speaker, Professor Eric A. Davidson, Fulbright Fellow USA, for their insightful and thought-provoking presentation. Your expertise and dedication to this critical subject have truly expanded our understanding of the complex relationship between agricultural practices and environmental sustainability. Thank you, sir. I would also like to extend my appreciation to the Honorable Vice Chancellor of KAU, Dr. B. Ashok, IAS, for the inaugural address and for taking the initiative and providing unwavering support in organizing this insightful seminar. A special thanks to you, sir, for your valuable time, guidance, and encouragement throughout the session. It's my great pleasure to extend a heartfelt vote of thanks to the Dean, College of Climate Change and Environmental Science, Dr. P.O. Namir, for making today's seminar a reality. On behalf of all, I want to express our deep appreciation for your leadership and dedication in organizing such kind of international seminars. We are truly grateful for the time, effort, and resources you have invested in bringing experts, faculty, and students together for this important event. Thank you, sir. A special thanks to our esteemed guests, Professor P. Indira Devi, ICR Emeritus Professor, and Dr. T.K. Kunyamu, Dean, College of Forestry. Without their presence, guidance, and support, this seminar would not be completed. A special thanks goes to our teaching staffs and non-teaching staffs. Your behind the scene efforts from organizing logistics to ensuring everything runs smoothly have been indispensable. And also special thanks to Dr. K. Prathapan, VC of DYPATU in Thailand, and special guests who have joined online and offline. Special thanks to Team DIS for the technical support. Finally, thank you all, the participants and students, for your attention and active involvement in question and answer session and the involvement in throughout the seminar. Your eagerness to learn and engage has been what made today's session meaningful. Thank you all. Thank you, ma'am. As we conclude this insightful seminar, I extend my gratitude to all our speakers, participants, and organizers for making this event a success.
Let us now conclude by paying our respect to our nation. I request everyone to please rise for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे